Oh, yeah, so by popular request, here is a little summary of the zoo. And there is too much unknown to put anything about complexity of those things, because sometimes we know something, but for strange variance for certain range of parameters, too long to fit on the margin of the slide. Before we start, any comments, any questions? And by the way, I can definitely post the slides. I can send them to you. I can post them on my webpage. And for that slide with resources, there should be links. And chances I've forgotten some very good resources. If so, tell me and I'll just add them to the slides before posting.
Just to be clear for summary, Volunteers KT has random access.
Okay. Correct me if I'm wrong, but I think generally it's okay to assume random access. So partially because some of the results of for cos KT for the version where you have an additional string, the conditional version, like the one we talked about for Krajcik's correspondence, they got some results in the regime when this additional vertex is way, way, way bigger than your x. And this way doesn't make much sense unless you have random access. So kind of, correct me if I'm wrong, but I think when in doubt, random access is the right thing to assume. Is it? Well, for Allenders, definitely for conditional K superscript T, definitely things won't work if you don't have random access, I think. But for others, I don't know. Yeah. But yeah, very good point. Yeah, so just kind of a plan. In the morning, I was going to talk about some very classical results, mostly about versions of mostly about MCSP, and in the afternoon I'll try to do impressionist sketch of some of the connections to cryptography and learning. That's the plan. And yeah, okay. So your somewhat friendly animal from your metacomplexity petting zoo, the minimum circuit size problem in France. So last time we talked about how to define minimum circuit size problem. I guess number of gates in a Boolean circuit over and or not. The gates don't quite matter. Circuits versus description size doesn't quite matter as far as I know. So this is kind of a weird problem because the way it's defined, the thing that we usually think of as gigantic is input. So this puts MCSP squarely into NP, which was definitely not very clear, likely with other measures. And this is because when your input is a whole truth table of your function, you're welcome to run in time 2 to the n squared, and, well, 2 to the n squared, generally polynomial on 2 to the n. That's a huge amount of time. You could do a lot of stuff in this setting. Also, it seems, because MCSP has been a big, big mystery since forever. So first of all, just to remind you, it's in NP. And Lupanov tells us that there is always a circuit with the number of gates roughly 2 to the n over n plus little o of 1, I think, factor. And so you could always do the following. You could always guess a circuit. Now you got a circuit at size less than 2 to the n over n. You got 2 to the n things to check. Each of them you could check in the time proportional to the size of the circuit. So here is an NP algorithm that works in time length of the input squared, roughly, that allows you to guess and check a circuit. So MCSP, minimum circuit size problem, is in NP. Big mystery, is it in polynomial time? Is it NP hard? Well, we do know by way back when Ladner's theorem that there are problems, if P is not equivalent P, that there is a whole hierarchy of things between P and NP, except we only know how to get them by diagonalization. There aren't that many good examples of intermediate problems, graph isomorphism maybe. Generally, people who get something of sub-exponential complexity, whittle it, and eventually bring it all the way down to P. But for most of those things, you could prove that they're NP hard. And by Schaefer dichotomy theorem, if this thing were a constraint satisfaction problem, we would know that it cannot be between P and NP. It has to be NP hard. Here we don't know. Moreover, we don't even know much more basic things that a lot of time we take for granted, and we can take it for granted with NP-complete problems because it works, is a search to decision reduction. If you could solve satisfiability in, efficiently for whatever your notion of efficiently is, you could find satisfying assignments efficiently, right? If you could solve clique efficiently, that not really being a CSP, you could find, if you could determine this, if there is a clique of size at most k efficiently, you could find a clique of size at most k. It's much, much murkier with MCSP. We don't know. Very basic fact. I will show you in the afternoon some weird way of learning things approximately, but that's not quite the same as like on a search to decision reduction. Fairly recently, Rahul Ilanga did kind of a search to decision reduction, but only for formulas, and it uses some rare parameter like a number of near optimal formulas. So it's not like you're on a search. Yeah. Oh, you improved? What is?
The search to decision for minimum formula size problem. I think it's like 2 to the n plus s, where s is the formula size.
2 to the, 2 to the n plus s, where s is a formula size.
Yeah, I think.
And it's which paper is it?
421, I think.
Oh, okay, so this is you with Rahul Santanam and with somebody else, or what is? Oh, it's just Rahul Ilanga. Okay. I thought it's your paper where you did. Okay. Yeah. Okay. So apparently in 21 it was improved, but yes, but for the circuit size we still don't know, right? For circuits we still don't know. Okay. Yeah. So just to say, yeah. So what's the exact parameters?
I think the time that is like 2 to the n plus s.
2 to the n.
For linear type formula.
Oh, and the s is not in the exponent?
Yeah, 2 to the n plus s.
2 to m plus.
Bracket n plus s. Yes, bracket.
Okay, s in the exponent. That's pretty. That's pretty big one, but thank you so much. That's cool.
So yeah, I have a hard time understanding. But it's 2 to the s should be constant, right?
2 to the 2 to the s, you could brute force.
Oh, I think brute force is a 2 to s log s.
Ah, okay. So rather than 2 to the s log s, you have 2 to the n plus s. Great. That's really cool. That also shows how non-trivial this problem is. Yeah, thank you so much, Hanlin. Okay. So, natural question to ask, is it likely to be in polynomial time? Is it likely to be NP complete? What do people believe? And in the year 2000, Valentin Cabanets and Ginny Tsai have shown an interesting thing, and I'll probably talk about this a bit more in the afternoon when I introduce the techniques. If you could put a minimum circuit size problem into polynomial time, honest polynomial time, then a lot of strange things happen. The first thing that happens is that cryptography as we know it mostly goes out the window. And the reason is intuitively, if you have a one-way function, that is something that's easy to compute, hard to invert. You could tell that something came from an output of a one-way function just because you would have a small circuit computing a function and you would not have a small circuit computing a random output. Using the connection to natural proofs, again, I'll talk more about it in the afternoon, they've showed that no one-way functions, you could factor things that we don't know how to factor efficiently, mainly because it's considered to be an example of the kind of generator that having an algorithm for minimum circuit size problem kills. So Blum integers is when you have something that's like two things, okay, let's see it. Do I really want to define it? Anyway, just to say Blum integers, this is a product of two primes such that we don't believe that it can be factored easily. So this is, if you want to think of one-way functions, one of the possible ones is factoring. You take two numbers, it's very easy to multiply them. We don't really know if I give you their product how to get back the numbers, even if you know that those are primes of a specific form. What else is the class e to the np has functions of maximum circuit complexity, and I think currently best known is just a touch above it, right, from your paper. I mean, do you know if there are any improvements? There is like not all the way down to e to the np?
For e to the np, we don't even have linear, like superlinear type program.
Okay, so for e to the np, Lin says no superlinear type lower bound. For just slightly bigger, they very recently, like within the last year, have proved a breakthrough result showing the near maximum complexity. Very beautiful paper, very beautiful result. Okay, so why would we even start thinking that MCSP may be easy? Well, we do know that in some cases we might be, if we replace general circuits with some very, very restricted things, we might be able to figure things in polynomial time, or at least kind of approximate them. So one example, I don't know if there are more examples that are squarely in polynomial time. is that if instead of circuits you talk about decision trees, yes, you could figure it in polynomial time, minimum decision tree using dynamic programming, but Bruno showed that it's still hard. It's still a hard problem. We cannot do it in NC1, right?
Yes, but just a remark, you can actually do it in depth log n, log log n.
You could do it in depth log n, log n,
It's almost an NC1.
but not an NC1.
But it's NC1 hard.
Okay. You could do it in depth. Bruno says we could do it in depth log n, log n, but it's hard for depth log n. So it's still kind of hard. It's not all the way down to being able to do an AC0.
What does hard mean here?
There's an NC0 reduction. It's hard under NC0 reduction.
It's hard on the NC0 reductions for NC1.
For NC1.
Yeah.
Like there's a very, 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 very simple reduction from
general SP to, so reduction from what?
no, for evaluating an NC1 circuit,
Okay.
right? So you give me like an NC1
Oh, I
circuit,
see. Oh, hard for NC1. Okay.
right? And now I come on from this circuit, I give you a truth table, and from the complexity depth of that truth table, I learned the output of the circuit.
Okay.
Thank you so much. So you just you could reduce evaluating NC1 circuits in NC0 to getting the minimum decision trees, right? Yeah. Very nice result. For now, so I'm going to talk a lot about DNFs today because this is one class we tend to understand a little bit better than others. And for DNFs, so or of and of variables, negated variables, we do know that you can approximate to the factor of n, I think, by doing a greedy algorithm, greedy set cover. So basically, you try to come up with a term that covers as many ones as possible. When you cannot do it as a term anymore, you got like a maximum, what's the name for it? Principal implicant. Then you move on and try to cover the remaining ones, and you can keep doing it. And there is a proof that you could approximate it to within the factor of n. I think there are also examples where this algorithm doesn't do any better. Okay? As far as I know, I cannot think of any more examples where we know that computing minimum something is easy. Oh yeah, OBDDs, okay, that's very true. OBDDs is another good example. Yeah, for the fixed order at least, right? Actually, I don't remember. Okay. Some OBDD problem is easy. Okay. So, natural question, how do we prove this stuff is hard? We prove the stuff is NP complete. And this is where things become really murky, because the notion of what it means to be NP complete has evolved a lot since the time that Gary and Johnson wrote their book on NP hardness. So what does it mean to be NP complete? Well, you could say I take satisfiability and I reduce it to my problem, right? That's how we usually do it. So what does it mean to reduce something? This is a picture that probably you've seen, or draw something like this when trying to explain reductions in your classes or to your friends. So you have some functions, it's efficiently computable, it takes things in the language L, in this case SAT, to some things in the language L prime, and things that are not in L get mapped to things that are not in L prime. And you don't need to hit everything in L. So why is it L? It should be L prime. Yeah, corrected. This should be L prime. And this, well, SAT, we call it L. Okay? So far, so good. And this is your classic many-one or mapping reduction. It's been around for a long time. Can be shown that things are recursively enumerable, semi-decidable, whatever you call it. And you could say things like SAT is reduces to L if there is a polytime computable F, such that every X is satisfiable formula if and only if f at X is L. Now you're thinking, yes, I know it. I've known it from my kindergarten class in complexity. Why? First of all, one thing that you could do with it, the first thing to play with, and this is the one Bruno was just mentioning, you could look at reductions that rather than having polynomial time computable f, have f computable different functions. And sometimes it's very useful because if you're talking about things being hard for complexity classes smaller than polytime, well, you don't really want to use all of polynomial time because it will basically solve the problem for you, and that's not great. But then you could also say something like that, well, actually, I really want to try to avoid having reductions that just solve my problem. And people came up with notions of natural reductions and notions of honest reductions that kind of try to avoid that issue. And both of them are roughly saying that if you have an input of a certain size, your output should be polynomial in this size, not much more, not much less. You cannot produce just two values as your output. You cannot produce very small values. And moreover, a lot of reductions we know have even stronger properties. The size of your output actually depends only on the size of your input. You'll see an example, but I don't know, let me think of something. Like if you're reducing satisfiability to, I don't know, what's your favorite clique, independent set. If you have m clauses and n variables, well, you draw this many, like 3 sets, let's say. You draw this many triangles, doesn't really matter what goes into each clause. Your size of the output really only depends on the size of the input. And I'll show you a reduction very quickly, which will be that very nice kind of reduction. But here is the issue. If MCSP is hard under those kind of reductions, then a major lower bound result that implies stuff, a lot of stuff, is proven. Well, okay, this particular, depending how strong the result is, but if NP is NP hard under those natural kind of reductions, then there are functions computable in linear exponential time that don't have polynomial time circuits. And that would be great. It would give some de-randomization, it would give a lot of stuff, it would be really cool. We also know, okay, in general, later on, Cody Murray and Ryan Williams showed that if MCSP is hard under your normal reductions, like I think polynomial time computable many-one reductions, then at the very least you need to show that you cannot solve everything in exponential time using a little bit of randomness in the zero error regime. I'll define ZPP in a second. We do believe it's true. Actually, a lot of people, if you ask them, kind of believe that randomness doesn't help that much, and probably everything you could do in ZPP you could already do in polynomial time. I don't think I don't even know of a good example of something that I know to be in this class, but I don't know to be in polynomial time. If you, anybody knows?
Partial matching?
Which one? Partial matching?
No.
I don't know. Maybe? Could very well be. I was just trying to look it up right when I was writing this slide and I couldn't find anything.
You're doing up with weights 0, 1. You want to find complete matching of the weight exactly case. Because it's often in polynomial random time, but it is not at all.
Polynomial random time with 0 error?
Is it 0 error?
No. Okay, sorry.
Yeah.
Oh, I think there are some natural search problems or position problems.
Yeah. Which search problems do you have in mind? Well, a lossless code. Okay.
Also, I give you a function from n+1 to n bit, and then go back to n+1 bit, and you need to find something that doesn't go to itself.
Oh.
But that's a search problem, not a decision problem.
Let me write it on the board. That's a nice problem. So you have 2n and n, and you want to find
Something that doesn't go back to itself.
find something here that doesn't go back to itself, right? Yeah. Yeah, very nice. So in search, so let's call this whole thing f. Find x such that f minus 1 of f of x is not equal to x, right?
I think you have one map from 2 to n.
Yeah, I'm, okay. But anyways, I'm combining those two in a, but yeah, that's
But that's the only example of
yeah, very good. So ZPP, we kind of do believe that it's very, very, very close to polynomial time. We cannot separate it from exponential time. We separated polynomial time from exponential time well before I was born, or I would imagine pretty much everybody in this room. Goes back to hierarchy theorems, Hartman, Stern, 60s. And so it is believable, but it's hard to prove. We haven't managed, and not for the lack of trying, as far as I could tell. Murray and Williams also show, I think unconditionally, that if your reductions are very, very local, I guess very similar to the kind of reduction that Bruno was mentioning, that you just can't do it. Cannot show that it's in peak and hard. Okay, I wasn't sure whether I should be sketching this proof or not, but here is the intuition. Suppose you make your problem, suppose I redefine MCSP to make it a little bit easier, rather than, you know, like there is a clique where you have k as a parameter, and then you have a half clique where you say on half the vertices I want a clique. Let's do the same thing with MCSP. Let's just fix S to be a parameter. And suppose there is a reduction from SAT to MCSP with a certain parameter S. Well, if there is a reduction and your S is small, great, you could solve SAT in better than exponential time. Killed off strong exponential time hypothesis, maybe exponential time hypothesis. Good luck with that. Okay, but suppose you set your S to be really, really big, like half the maximum size, maybe. Then you map satisfiable formulas to something that have smaller circuit complexity, and you map unsatisfiable formulas to strings which have nearly maximum complexity. Great, we always wanted to have a maximum size string in E, and here is the way to construct it. So this is kind of the intuition. This is sort of the general intuition, I think, at least to me, why it's really tricky to reduce things to MCSP, because you know instances give you hard things, give you random things. And we know most things are hard, getting our hands on the hard thing is difficult. It's like, okay, it's a little bit easy and continuous fault. We know that there are very, very few rational numbers. Most numbers are irrational. Getting our hands on the rational numbers, well, okay, we could take square roots, but still, it's not obvious. Here, it's even worse. We don't even have an analog of, let's take a square root and you get something irrational. Okay, any questions, any comments? Do you kind of see the intuition why proving that things are that MCSP is NP hard conceptually runs into issues? So there were lots of barriers results. I think, Bruno, you had a barrier result way back when for proving related stuff is NP hard. You cannot do it under black box reductions, so there are lots of barriers. Okay. So we will today talk about restricted classes of circuits and see what we could do. But let me just digress for a moment and talk about what's efficient. What is an efficient algorithm for you? For the longest time, we were thinking about efficient algorithm as polynomial time. Probably if you ask cryptographers at least, they may somewhat disagree because they tend to use randomized algorithms and they cannot do without. And in fact, the randomized algorithms as an alternative notion of efficiency keep cropping up a lot. So I will talk about Russell and Pagliazzo's possible world scenarios of resolving P-verse and P question. And already in that old paper, he says, well, it could be that everything in NP is efficiently solvable. And by the way, I don't quite mean that means P equals NP. Maybe we just have efficient randomized algorithms. And for practical purposes, it's good enough. So what is happening in the field, it seems, is that sometimes when you have those barriers, you could circumvent at least some of the barriers by using randomized reductions, by using randomness. Again, it's not your conventional definition of what it means to be NP hard, but hey, we know that for MCSP, getting the conventional definition of NP hard, like either is really hard to do or just doesn't work. Okay, just to flash this slide, how many people have seen BPP? Okay, so I don't need to flash the slide. So just to mention for BPP, we do have an example which we don't know how to put in polytime, and if we could, we get lower bounds, and this is polynomial identity testing or factoring polynomials. I give you polynomial of a finite field, for example, ask you, is it identically 0? There is a very nice randomized algorithm. We don't know how to do it deterministically, and if we do, we get lower bounds. This goes to Kamenets and Impagliaz, is this 01 or early 2000s? Okay. And I already gave this speech, but just to say it again, it would be really cool to get our hands on an explicit hard function. in linear exponential time. Because if we do, then all this conversation about bounded error, one-sided error, two-sided error, zero error, randomness helps sometimes. Is this reduction really NP if it uses randomness? This goes out the window. Because if you could get a function, just one construction that you could do in linear exponential time of a function of a circuit size, a big circuit size near maximum, then you can de-randomize. You can collapse all of those randomness classes to polynomial time. And the intuition is that if you can get a true stable of a really hard function, remember way back to Kolmogorov, hard and random are pretty much the same. You could use it as a source of randomness. And I'll show you probably in the afternoon if you get there, a specific construction that can do it, Nissan-Dickerson generator. How many of you have seen Nissan-Dickerson generators? Okay, so would it be interesting for people to see one? Okay, great. Okay, you may say, oh, so that PP equals X, we don't know how to prove it, but can we at least say what happens if we could solve MCSP in this class? And in Polyazov, Kabanets, and Volkovich showed under an additional cryptography assumption and indistinguishability obfuscation, which I could define, but I don't particularly want to get into it. With this assumption, and people think that maybe, possibly, they might be able to construct this thing. MCSP is solvable with randomness efficiently if and only if satisfiability is. Okay, questions, comments? So all this was about like what's the big deal about another NP completeness reduction? Well, this one would be very unexpected, would give you lower bounds, would give you a lot of cool stuff.
Sorry, I'm missing something like this about the this is because of randomized reduction.
So random, yeah, but you also need indistinguishability obfuscation. It's a little bit, it would require some time to explain.
Okay.
Okay, so let me just talk about special cases. We cannot solve the thing for general circuits. How long can we go to be able to solve it? Bounded depth circuits are about as large a class for which we know anything. So not circuits, I'm sorry. Bounded depth formulas, not even circuits, is the only class for which we know something. But I'll flash this slide just because I will be mentioning those things on the later slides. Yeah. Okay. Oh yes, so talking about circuit complexity classes. So one thing to say is that, yeah, that's why I'm flashing this slide. You could say, okay, we don't know how to solve, whether we could solve a minimum circuit size problem in polynomial time. Do we know that we cannot solve it like in a really, 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 really low complexity class? We kind of do. And again, Bruno showed for decision trees going below log depth bounded finite circuits would be an issue. For MCSP, you could show something interesting. First of all, you could show that you unconditionally cannot solve it by bounded depth circuits even with parity gates or like arbitrary prime gates, but generally with the intuition is with parity gates. So we know it's maybe simple, but it's not that simple. And this is still well below and see ones for which Bruno has shown the reduction. There is something even more interesting that's going on. Chergachi, Cabanet's-Lu, and Mirisiotis show that pretty much every time we know how to prove a lower bound for some function, for parity, for majority, you name it, we actually can adapt the techniques and show this lower bound for MCSP. To me, conceptually, this is a really cool result. It kind of says that MCSP is almost morally your ultimate hard function. Yeah, pretty much. Basically, stuff that you could do with switching lemmas, with shrinkage, with local and W generators is exactly what you could do with this. Yeah. On the other hand, if you have very, very, very local reductions, you cannot even reduce parity to MCSP from Murray and Williams. Okay. Any questions? Any comments? So if you ever need to prove a lower bounds, you could try doing it for MCSP, and if you prove it, great. Okay, back to special cases. So where do we know NP hardness? The NP hardness for finding the minimum size DNF had been known for a very long time. It's by Masek, and from what I understand, it's never been published by Masek, but it appears in Gary and Johnson. And I will show you kind of one of the later versions of this reduction in a moment. And this is a very, very standard kind of reduction with all the good properties you could think of. Only pretty much, 40 years later, Hirahara, Oliveira, and Santana extended it to add a layer of parity gates. And they could show that NP hard to find a small circuit of this kind, given a truth table. With a lot of extremely heavy machinery, Rahul Elanga managed to get the bound for any constant d of depth d formulas, not even circuits. It's randomized, it's quasi-polynomial, it's Turing reductions. It uses like a lot of tools in the toolbox to even get this kind of NP hardness. And just, 3 years ago, there was a major breakthrough when Shuichi Hirahara showed that if rather than dealing with total functions, you are trying to find minimum circuit size of a function that matches a given truth table where there are a lot of don't cares. He managed to show that this is NP hard, and it's also under randomized but many-one reduction. It's a beautiful proof. It uses a lot of heavy-duty machinery. It uses secret sharing schemes and stuff that haven't been done before. It's a very cool thing. And also a variant of one of the beasts in the zoo, conditional cause complexity, where you fix a bound or give a bound as an input and ask what the minimum machine that prints X, given the description and also given an auxiliary input in time t. That had been shown, I think, by Liu and Paz in 21. It's the proof uses some interesting things. For, in particular, that auxiliary string that they're getting is huge. It's bigger than t of length of x is like really huge. You can't really read the whole thing. In that regime, they've shown NP hardness. Okay, questions? Want to see some NP hardness reductions? Okay. How many people have seen PAC learning? Not everybody. Great. So, I'm not going to the dark side of AI, but PAC learning had been defined by Leslie Valland way back when to talk about the problem. You are given some samples, let's say some are positive, some are negative, and you are trying to come up, and maybe you're even given a promise that the samples come from a function from a certain complexity class, and you're asked to compute a hypothesis, which may or may not be from the same class. That's probably approximately correct compute set. Probably means if sometimes you don't output the hypothesis that does the right things, it's okay as long as you only do it with probability delta for some small delta. Approximately means even when you produce something good, it doesn't have to be correct everywhere, it just has to make a mistake with probability epsilon. Probably approximately correct is a great term to make your colleagues and friends wonder what you're doing. Oh yeah, I'm working on probably approximately correct learning stuff. Yeah, right. It's hard. We'll show it's hard. And so proper learning is when whatever you return is actually from the same class from which you promise a function came from. There is also agnostic learning when you're not promised that something comes from the class. You're just trying to get something that's as close as possible to the best thing in the class that approximates your function. Okay? And this is a framework. You have a learner that can keep pressing the dispenser button, and every time it presses the dispenser button, the button drops a random example. Crucially, in original Valland setup, it's from arbitrary distribution. You don't know the distribution, but a lot of the results that's been proven are either for uniform distribution. Sometimes that's the only time we know how to do stuff or how to prove stuff, or for a distribution that's sampleable, polysamplable, which means your dispenser is a circuit of polynomial size that takes an input and produces, which is randomness, and produces a corresponding sample according to the distribution. Questions, comments? Okay, let's try to probably approximately figure out some stuff. Oh yeah, so before I go that, let me just show you how it's different from MCSP. In MCSP, the standard one, we're talking about decision problem, although search problem is also fair game. In PAC learning, we're pretty much talking about search problem. In MCSP, the way we've defined it, you get your whole truth table as an input, you have plenty of time. In PAC learning, you really want to run in polynomial time, so you only get to see very, very small fraction of samples if you're over uniform distribution. And in this setting, I'll talk about the setting when you can actually ask for specific samples, but in this setting, you have no control over what you're getting. Just press the button, out comes the sample. And in CSP, you want something in your class. Here, you don't really have to. You may output, you're trying to learn a circuit, you may output Fourier coefficients. It's still okay. It's better than we know in a lot of cases. And MCSP, you could talk about approximation versions, but generally, when you state MCSP, you really want something exact. Here, you explicitly from the beginning only want to agree with probability epsilon. Questions? But morally, they're similar, and I'll probably show in the afternoon if I get to it, how you could actually use hardness of MCS, use easiness of beta complexity problem to do some learning. Okay, I have 20 minutes, and it's time for an NP hardness reduction, yay. So this version is from a paper from 2008, I think, where they did a lot of stuff. I guess original proof goes back to Pitt and Valiant, but this is the one that I got. So I want to reduce recolorability to learning DNFs. And the way I'm going to do it, the reduction will take a graph and construct a list of samples such that there is a DNF with 3 terms, like it's something or something or something, that agrees with all the samples, as in it evaluates to true whenever the sample. Samples will have as an input the list of values of the variables in the DNF, and as an output whether the DNF is supposed to evaluate to true or false. And there will be a DNF which agrees with all of such samples if and only if the original graph was recolorable. Is that okay? So now I'm not even talking about pack learning or anything like that. I'm just taking a problem of recolorability and I'm reducing it to existence of a formula of the form end of stuff or end of stuff or end of stuff. And here's how I'm going to do my samples. I have a graph on n vertices. I introduce a variable for every vertex. And now for every vertex in the graph, I'm going to put a sample which is positive, on which my DNF has to evaluate to 1, where I make all the variables in my sample 1 except the variable corresponding to the vertex. So like if I have the graph like this, what is it, 5 vertices, I'll have something like 0, 1, 1, 1, 1, and then it would be true. 1, 0, 1, and so on up to 1, 1, 1, 1, 0. So I get n of those things, okay? That's how I'm doing my vertices, and now I'm doing edges. And the edges I'm doing essentially the same thing, but for every edge I'm putting zeros in the 2 endpoints. So for example, the edge 1, 2 will look like 0, 0, 1, 1, 1. And here I'm marking it negative. Is it clear what the construction is? One thing to notice here, I am getting the number of samples to be the number of vertices plus the number of edges. So if you encode your graph by the list of edges, it's a very, very local, very natural reduction where the size of the output only depends on the size of the input. Questions or comments? So now what do you do with this thing? You prove that it works. So I want to say there is a 3 coloring of the graph if and only if there is a 3-term DNF that agrees with the sample. So first of all, suppose there is a coloring. Here is my DNF. Can you actually see this thing? I will put in the first term everything that's not red. In the second term, everything that's not blue. Third term, everything that's not green, or whatever the colors are. So first notice, I want everything positive because I want to be able to change one variable value positive to negative, and the DNF goes from true to false. Now, suppose, okay, so let's take a vertex. Tell me a vertex. That you, which vertex do you want? Okay, a red vertex. So for the sample, I think it's sample number 1, corresponding to the red vertex, the very first term, okay, so let me try to parse it one more time. So there is only one red vertex. So I'm putting in the first term x2, x3, x4, and x5. If I look at the first thing, the first term evaluates to 1 because I did not put the only thing that's a 0. Now, suppose I have an edge, like edge, I don't know, give me an edge. 1, 5, okay. So how do I prevent two things being the same color? So let me see how I could say it. Suppose I have an edge 1, 5 and I plug it into my DNF. So there are things that are not orange, and there are things that are not green. And at least one of the terms will have not orange and not green, and that indexes is 0. So every term has something that, sorry, there is only one term that has, I'm not saying it right. So two variables have different colors. If they would have the same color, it would evaluate to 1 because they would go into the same term and another term would be satisfied. This way, no matter what term you take, it's either not orange or not green. Yeah. Okay, is everybody happy with the reduction? That's about as far as I'm going into proofs. And you could do the other direction, which is a little, I wouldn't say it's trickier. First, suppose somebody gives you a 3-term DNF that agrees with all the samples. You just take the first color such that the vector corresponding to that color, one of those top vectors, satisfies the term. And again, things have to be positive because you want to go from positive to negative by switching things from 1 to 0. So you don't really have negative literals in here. Any questions? Any comments? Do you kind of agree that it works? So it's a very simple reduction. It's exactly the kind of reduction which we cannot use for MCSP. Because it's very natural, the size of the output depends only on the size of the input. It's very local. The only thing you need to construct a sample corresponding to the edge is, well, the edge. And those you don't even need to look at the input, you just need to know how many of them there are.
Just one question. Like, the previous slide is about hardness of learning, right?
Sorry?
The previous slide is about hardness of learning, right?
It's the next slide will be the hardness of learning.
Okay.
Because I didn't yet tell you why this shows that proper learning DNFs is NP-hard.
Okay,
Sorry, I shouldn't say NP-hard. NP-hard will be for the mean DNFs. It will be hardness in a sense that if there is a randomized algorithm to pack learn 3 terms DNFs properly, then you could use this algorithm to solve 3 colorings, so all of NP can be solved efficiently randomized. Again, apparently efficient is randomized. Okay, but I didn't show you the slide. And this is a slide that says why it shows that it's hard to, why it tells you anything about pack learning. Suppose you have an efficient randomized algorithm to pack learn. And then you do the following. you ask the algorithm to learn a 3-term DNF properly. Suppose it gives you a 3-term DNF. Now you could check yourself whether it fits all the samples. What you do know is if such a DNF exists, with probability 2/3, you get something that fits the sample, because your probability of outputting a hypothesis that's way off is at most 1/3. You could put your epsilon parameter to be like small, half the size of the graph, so it's very unlikely you make an error. And so if your algorithm gives you something that you could check matches all the samples, then you know there is a 3 coloring every time. If it gives you something that doesn't match the samples, maybe it made an error, maybe there is no coloring, but probability of there being a coloring and it making an error is just 1/3. Therefore, here's an algorithm that works with probability 2/3 and you know, solves 3 coloring.
How large is the truth table?
We are not doing truth table. Here are all the samples. Yeah, so this is why I was talking about pack learning first, because to deal with truth table, you need extra pain. But here you just get something of size number of edges plus number of vertices times number of vertices times number of vertices plus 1. Yeah.
Why do you need proper learning here? Like, because the second check you could do for any age, right?
Because you want the learner to give you a 3-term DNF. If it gives you a list of Fourier coefficients, I don't know what to do with it.
You want to evaluate, right? Do you need to really see the DNF?
I don't know if you really want to see the DNF, but you want the learner to return something that's a 3-term DNF. If it returns you a n-term DNF, then it's not very useful. Because you can actually get an n-term DNF, 3 n-term DNF yourself. That kind of approximates.
Because you know that this 3-term DNF exists. Oh, I see.
Yeah. Here it really uses the fact that it's proper learning. You are promised 3-term DNF and you're getting a 3-term DNF.
Okay.
Yeah. And yeah, as I said, with greedy set cover, like bigger DNF you could get yourself. Okay. So this is essentially the idea that's being used in proving NP hardness of finding the minimum DNF. Just to say one thing which I should have put on the slide, but then I didn't want to. At this point, you may be saying, wait a moment, why do we really bother with the case of the truth table? What if it's just doing circuit minimization? Somebody gives me a circuit and asks me if there is an equivalent circuit of smaller size. Then, first of all, you're out of NP. Because you know, now your input is polynomial size potentially, and so you don't have all the time in the world to check that the two things are equivalent, for example. And it was shown way back by Buchführer and Ummans that for the formulas, like I give you a formula and I ask you whether there is I give you a formula and a parameter and I ask you if there is a equivalent formula smaller than parameter. I think it's a sigma 2 complete. Does that sound right? So it lives around the second level of the polytime hierarchy. And I think for decision trees, given a circuit, is there a decision trees of size smaller than S? Brunner just proved that it's what, p-space? P-space. P-space complete. So, I mean, you may think like, you know how to construct those decision trees, but if I just give you a small circuit and ask give me a smallest decision tree. Bruno says you go all the way up to p-space. Okay. So, oh, I only have 5 minutes. Okay. The ideas behind the NP-hardness DNF are very similar. You start with set cover rather than tree coloring. And to make life easier, you start with a very special kind of a set cover where every set consists of exactly 3 elements. Moreover, you partition your elements into 3 equal groups such that every set takes 1 element from each group. It's still NP-hard, and they even got some approximation results out of this. So there are 2 things that they're doing. First of all, this thing does not give you a total function. If you have a truth table, you kind of expect it to give a total function. What they do, they first say, if I have a truth table with don't cares, then finding the minimum DNF for it is NP-hard. And the second idea that they're using is you cannot do those vectors anymore, because if you're doing the truth table, you get way, like, those things of having n variables means you need the truth table of length 2 to the n. Suddenly your instance of size n becomes the instance of size 2 to the n. Good luck doing it with polynomial time reduction. So what they do instead to account for this is, rather than dealing with length n vectors, they pick roughly length log n vector, more precisely pick a number such that q choose half q is at least 10, like the smallest such number, and then make a vector, unique vector for each of your things by taking exactly half of ones in different places for different vectors. And then you make something of length 3 by sticking things from the first part in the first block and so on. And then they do pretty much the same thing. And this is too fast, but any questions, comments? So let me tell you the more interesting things. How do they deal with the fact that this is a partial function? And the thing that they do is really cool. They say, let me define a new function. I throw in 2 new variables. And for some of the don't knows, I will actually put a value depending on the parity of my x. Parity, our favorite function, the function that we know is super hard to compute by DNF, as hard as it gets. What does it give you? You really need to add the number of terms corresponding to the number of your stars to account for that third case, for the bold case. And this is because, well, that's what it takes to do parity. You can't get away from just writing, oh yeah, if my x's are like this, corresponding parity is whatever, then I need like whatever, y or not, y2, not y2. This is the idea, and then they say, well, now my new thing is of size number of stars in the old things, because parity, plus the original size, I can figure out the original size. Well, yeah. It also, yeah, they also do it for approximation, right? I don't remember.
Because this number of x terms should always be the same, right? The only thing that now varies is
Exactly, yeah.
so this should hurt your approximation. Unless the number of stars is small.
Yeah, they do something for approximation. I'm kind of blanking what they do. The approximation was then improved by Feldman using polynomials and stuff. And in any case, you could always greedy approximate to the factor of n. I think the log n factor is when it becomes hard, and I think that using some tricks, they might still be able to recover something like little under log n, log to the gamma n factor, something like that. I'll have to look at the paper. But Feldman then improved the approximation later, I think. Yeah. In any case, what was interesting about this to me is that very recently, Shuichi, using a lot of very, very, very heavy machinery, have proved that partial MCSP, the one where you have don't cares, is NP-hard. But if you work in the general circuits, you don't have that nice things, oh yeah, parity, it will always have maximum number of terms. I wish we had something that would have maximum number of terms, we'd be done with our de-randomization. This is kind of the thing that, one of the things that's crucially missing in our attempt to prove hardness of MCSP as a total function. That's why the DNF thing doesn't work. And I'm out of time. Questions, comments? Yeah, so there is a lot of work on approximation of those things. I'm kind of sweeping it under the rug because there is just a lot to talk about. Okay. Thank you.